Hi, everybody. In this lesson, we are going to be taking a closer look at materials and specifically the properties that make certain materials ideal for certain situations and applications, and the methods that are used to test materials to determine those material properties. So let's get into it. When it comes to material testing, there are a wide variety of different tests that are used to test for different sorts of properties. To try to characterize these in broad terms, we have static testing, which looks at a material's response to a constant loading condition. We apply a force, hold it under a constant force for a while. Or we have dynamic testing, where we look at a material's response to varying load conditions, including changing the magnitude of the load, cycling that magnitude on or off, as though to simulate traffic driving over a bridge where it's carrying weight, it's not carrying weight, and so on, and the mode of applying those forces. Some of the properties that we're going to be looking into and trying to understand are maybe words that you've heard in everyday language, but you might not understand the technical definitions for these things. So we're going to start to understand what these actually mean in terms of material characteristics and how they're measured and how they are how we explain them visually. So some different properties, mechanical properties of materials that we might be interested in are their strength, resilience, toughness, ductility, malleability, brittleness, deformation, fracture, and all of these have to do with how they comply with different design requirements. Of the many kinds of tests that are out there, the ones that we're going to focus on primarily include tensile testing, compression testing, and hardness testing. I'm definitely going to spend lots of time talking about tensile testing, but the others are definitely worth looking at too. So compression testing is when we put an object, a shape, a piece of material under compressive loads, meaning we're going to squeeze them, we're going to apply pressure to them until we observe failure, material failure. And we'll talk about what that means. Materials under compression are prone to what's called buckling, where they just sort of give out and flop over, like if you squished a bendy straw. So for compression testing to be valuable, we need to make sure we're using samples with a large cross-sectional area so that they won't bend and buckle, and instead we actually get a look at their compressive strength. And as the compressive load is applied, we'll see the sample stretching out, squishing outward, and making its cross-sectional area larger until ultimately we see rapid deformation and failure. The hardness of a material is its resistance to permanent deformation, so resistance to things like scratching and wear and tear, cutting and drilling, and so forth. Some materials are really prized for their hardness. Things like cutting tools, for instance. If you need to cut something, you have to use a tool that's harder than the thing you're trying to cut. So, very, very hard materials, like, for instance, diamond or tungsten carbide, are used to cut some of the hardest steels and things like that that we need for industrial purposes. So, the method for testing the hardness of a material is actually a couple of different methods. One of them is called the Brinell hardness test, in which a very hard tungsten carbide ball is held with a 500-pound force for 15 seconds against the material. Then, when the ball is removed, the resulting crater gets measured and compared to other materials, and we're able to determine how hard that surface material is. The Rockwell hardness test is really similar, except instead of the tungsten carbide ball, we have a pointed diamond tipped cone that's forced into the test sample by a predetermined load. Again, the depth of that penetration is going to be measured and compared with other materials to determine how hard that material is. When it comes to tensile testing, this is another variety of tests which we would call uniaxial loading, which means that a load is going to be applied in a straight line. And this could be compressive, but in this case, we're talking about tension. We're pulling in one axis only to observe how the material behaves under that tensile load. Tensile testing is also typically a destructive test, meaning that we're going to apply that force to the sample until the sample fails. To perform a tensile test, we need to have a standard test sample of the material in question. And due to their shape, these samples are called dog bones. and they're just a sample of the material that's been machined down to exact dimensions that we can secure in our tensile testing machine and pull until we see that failure. But making samples this way ensures good, meaningful, reproducible results, and that's the key thing. As we're going to see, we have a couple of methods that we use to ensure we are collecting valuable information about the material that's being tested and accounting for any variations that we might have in the size and shape of the test sample itself, because we're not interested in the strength of the shape that we're testing. We're interested in the strength of the material. So the dog bone samples are machined down to an exact diameter or an exact cross section that we can measure very accurately, and then it's secured in the tester, and the tensile load is applied until we observe that material stretching and ultimately fracturing. As the machine tests the sample, it's constantly collecting data, collecting measurements of the amount of force being applied and how much that sample is elongating. So it's going to use that data to create a plot like the one shown here. On the y-axis is the force applied, and on the x-axis is the elongation. That little symbol there is the lowercase letter delta. And all that is telling us is how much longer that sample is getting as force is applied. And as you can see, initially the relationship between the force applied and the elongation is linear. After a certain point, it stops being linear and it really takes off stretching more with a relatively small increase in force. So one of the key pieces of this lesson is going to be understanding this curve and really digging into how to read and understand it and interpret it to learn more about the materials being tested. Here we have two samples of the same material. Sample A and B are both alloy 230 red brass. Sample A has a diameter of 0.125 inches. Sample B has a diameter of 0.375 inches. The question is, if both samples are tested to failure, will the applied tension force and elongation be the same for both tests? The answer is no. Load elongation results are dependent on sample size. So larger cross sections will require more force to stretch. That makes sense. There's more material there, so it's going to take more force to stretch it out. This means that our test results are affected not only by the sample material, but also the sample size. So the next question is, how can test data be manipulated to represent a material and not be affected by subtle differences between test samples? In other words, we want to be able to isolate the material properties in our test and not have our data skewed by samples of different lengths or diameters. That brings us to two really key concepts in this area, which are called stress and strain. Again, two words that you might be used to using in your everyday language, but now you're going to learn the technical definitions for these. Stress is load force per unit area. We use the lowercase letter sigma to represent stress in formulas. Strain is the amount of stretch per unit of original length. So we use lowercase epsilon to represent strain. In other words, stress is taking into account the cross-sectional area of the shape when we're measuring the force applied to it. Strain is taking into account the original length of the material when we are trying to measure and understand how much it stretches. A really excellent primer for both of these concepts is here by the Efficient Engineer, so I'll make sure I include a link to this video as well. If you want to understand stress and strain more fundamentally, it's very much worth your time to give this video a watch. So once again, to eliminate test results based on sample size, we calculate the sample stress, or the load per unit area. This is the formula for calculating stress. Stress is equal to the load divided by the area, or the force over the cross-sectional area. So let's see if we can put this to work here. Here we have a diagram for a round cylindrical dog bone. See if you can calculate the stress in the cylindrical dog bone with a 430-pound applied tension force running down the length of the sample. To start, we can find the cross-sectional area. The dimension in the center here is giving us our diameter for the sample, 0.125 inches. So our area formula for a circle is going to come in handy, pi r squared, where the radius is 0.0625 inches. Square that, multiply by pi, and we have our cross-sectional area of 0.0123 square inches. Now we can plug that into our stress formula using the 430-pound tensile load divided by that area we just found. And that leads us to a stress of 35,000 psi. Stresses tend to be relatively large numbers. In US customary units, we're almost always measuring in pounds per square inch. In metric units, we would most likely be measuring our stresses in pascals or megapascals or gigapascals. Likewise, when we are looking at samples of different lengths, we can have a hard time measuring their elongation in a meaningful way. Longer samples will stretch more per pound of applied force. This means that our test results are affected not only by the sample material, but also the sample length. So, how can test data be manipulated to represent a material and not be affected by subtle differences in the length of the test samples? For this, we have a concept called strain. Strain is the amount of stretch per original unit of length. Elongation is simply how much longer did the sample get. But elongation is going to be different under the same applied force for samples that are longer or shorter. So in order to determine how much they stretch per unit of original length, we're going to use strain. Again, strain is epsilon. The elongation is lowercase delta, or you may see it as capital delta L, change in length, divided by the original length. So strain is the amount of stretch divided by the original length of the sample. So let's see if we can put this concept to work. Calculate the strain in the cylindrical dog bone with an elongation of 0.0625 inches, 1/16 of an inch. Now, the original length that we're interested in this problem is the 1-inch narrow portion that's at the center of the dog bone. That is where we're going to see stretch happening. So that is the area that we're going to consider for our original length. Our strain is going to be our elongation, given in the problem, 0.0625 inches, divided by our original length, which is given in the diagram of 1 inch. So our strain works out to 0.0625 inches per inch. That's what our unit looks like for strain. It's a unit of length per unit of length. You might be tempted here to have those inches cancel out and offer up a unitless answer here. But this is a ratio. It's a ratio of how much it will stretch per unit of original length. If we can calculate the stress and the strain in a sample that we've tested, we can plot those two measurements just like this, with stress on the y-axis and strain on the x-axis. It looks a lot like our earlier curve that was showing us force and elongation. But a force and elongation graph does not take into account differences in sample size. So if we instead calculate the stress and strain, we get a curve that should be remarkably comparable from one sample of a material to a different sample of the same material. In other words, each material is going to have its own characteristic stress-strain curve. In this portion, we're going to take a very close look at the stress-strain curve, and we're going to understand what different regions of this curve tell us about a material. And if you want a bit of a closer look at this, I highly recommend this video by The Efficient Engineer, Understanding Strength, Ductility, Resilience, and Toughness. When we apply a tensile load to a sample, initially the response is going to be linear. As more force is applied and as the amount of stress grows, the amount of strain that we see is going to be proportional. So we see this linear region at the beginning of the curve. We call this the elastic range, because in this range, the material will behave elastically. That means if the force is removed, the strain will recover and the material will stretch back to its original size without damage. As more force is applied, the relationship will continue this way in a linear fashion. This continues until we reach the point known as the proportional limit, where this elastic relationship between stress and strain ends, and we start to see what is known as plastic deformation. So this is the first region of the curve worth examining. Within the elastic region, we can determine the material's modulus of elasticity. This is a really key property about a material. It tells us how much it will deform under different types of loads. The modulus of elasticity is equal to the stress divided by the strain at any given point along this line. Without even considering any numbers, if we're looking at two different sets of sample data that are plotted on the same axes, we can tell a little bit that helps us compare the two materials just by looking at them. If this line is steeper, that indicates a material that is going to deform less under a force. In other words, a stiffer material. And if the line slopes more as stress is applied, then we're looking at a material that is more elastic and able to stretch more as force is applied. So which of these materials has the greater stiffness? Again, this elastic behavior is important. Within the elastic range, if the load is removed, the test sample will return to its original length. This is how engineers want materials to behave. They're going to stretch as forces are applied, but we want to make sure when the force is removed that the piece of material is going to go back to its original length, and we're not going to run into any issues with parts lengthening or stretching out of tolerance. Again, at the top of this line where the proportional relationship ends, that's known as our elastic limit. Beyond this point, any stress that's applied is going to start to have a larger and permanent effect on the length of the sample. This region of the curve also helps us understand a concept called resilience. Resilience is the amount of energy per unit volume that a material can absorb while in the elastic range. In other words, this is how much energy a piece of material can absorb before it deforms permanently. And resilience is defined by the area beneath the stress-strain curve, specifically in the elastic region. So if we find the area of this triangle, we have a number we can use to quantify and compare the resilience of two different materials. This is a function of the material's yield strength as well as its elasticity. So a material that has equal strength but greater elasticity is going to have a triangle here with a larger area. Materials that are stronger and more elastic are going to be more resilient. So the top of the elastic limit is a point of a lot of interest to us. It's called the yield point. The yield point, where the elastic limit exists, is where we start to see very small increases in stress producing a much greater strain. And this deformation after this point is permanent. So even if the force is removed, the elastic portion of the strain will recover, but any portion of strain past the yield point won't. This is the point at which an engineer considers a piece of material to have failed. It's important to note, though, that this doesn't necessarily mean that we've fractured. It doesn't mean that the piece of material broke in two. It just means that we have stretched it beyond the point where it's going to go back to the way that it was. So in engineering terms, this is what we call failure. This brings us to the plastic portion of the curve. All of the deformation that takes place beyond the yield point is called plastic deformation. This is unrecoverable, permanent elongation, where even if the force is removed, we're not going to see the sample returning to its original length. Only the elastic portion of the strain will bounce back. Again, plastic deformation represents material failure, not exactly fracture until we reach the end of the curve. But when the parts were designed for their given application, they were designed with very specific lengths and dimensions. And at this point, even if the force is removed, those parts are now outside of their allowable tolerances. They're longer than they should be in order to operate properly. What's interesting to note here on the curve is that as we get into plastic deformation, our test sample is continuing to elongate, and our cross-sectional area is starting to decrease. The sample is getting narrower where the breakage is going to occur, but at the same time, its ability to carry the load is still increasing through this range. So how is that possible? How is the material getting stronger while it's getting narrower. The simplest explanation here is that the weakest point keeps being stretched and keeps becoming stronger. This stretching and strengthening keeps occurring until the decrease in area overcomes the increase in strength. The point at the top of the curve is what is called the ultimate tensile strength. This is where the ability of the material to carry a load reaches its peak. After this point, the force required to continue straining the test sample is actually going to decrease. This is observable in the actual tensile test with a phenomenon called necking. This is where the diameter of the sample visibly gets smaller as more and more force is applied until eventually we see fracture. So which of these materials has the greater strength? After we reach the point of ultimate tensile strength, if continued force is applied, necking is going to continue and the cross-sectional area of our shape is going to continue to decrease until fracture occurs. Fracture is where our material actually splits in two. The plastic region of the curve tells us a little bit about the material's ductility. Ductility is the amount of plasticity before fracture. In other words, the greater the ductility, the more a material can be deformed in tension before it actually breaks. For a lot of applications, this is actually very advantageous. We usually don't want our materials to just instantly fracture after reaching their yield point. That would be what we'd call a brittle material. The idea of malleability is very similar to ductility, except that it applies to plastic deformation in compression. Malleability is the amount of plasticity before fracture when something is pressed, squeezed, hammered, etc. Which of these samples was the most ductile? A is the most ductile material, which we can see from the amount of stretching and deformation that went on before fracture. C was the least ductile because we see a really brittle shear where the material split, and B is somewhere in the middle. There's some amount of plastic deformation, but not very much. Brittleness is material failure with little or no ductility. This is a lack of ductility, but not necessarily a lack of strength. Brittle materials can be just as strong as ductile materials. That is, they can reach the same ultimate tensile strength. The difference is how they behave after reaching that point. Which of these graphs represents the more brittle material? The graph on the right shows the more brittle material. The graph on the left shows a more ductile material. In the ductile example, we see a lot of deformation in the plastic region of the curve, where in the brittle example, fracture occurs very shortly after we reach our ultimate strength. A lot of materials are prized for their toughness. Toughness is the work per unit volume required to fracture a material. This is similar to resilience, but resilience was the work per unit volume that a material could withstand before permanent deformation. Toughness also accounts for the energy that a material can absorb even during plastic deformation. Toughness is defined as the total area under the stress strain curve from the test initiation all the way to fracture. So this is a function of strength, elasticity, and ductility. A material that has high strength, high elasticity, and high ductility is going to be able to withstand a lot of work, a lot of energy. It's going to resist fracture even under lots and lots of stress.